Now, commonly used symmetric algorithms are going to be this, which stands for data encryption standard. It uses a 64-bit key, but only 56 bits are used for encryption. Triple this, which stands for triple data encryption standard, which because it's triple this, it means the key size is 3 times the key size of this. So it's going to be 3 times 56 bits. So triple this uses a 168-bit key, which actually it depends on the implementation. Each vendor, so triple this is not like it has a lot of options, because exactly as I stated on the slides in there, actually what triple this does is going to actually perform 3 times the encryption, or it can do 1 time encryption, 1 time decryption, another time encryption. So it's a lot of variation in there, but it's triple this is going to perform 3 times the this function. So that's why actually, as I said in there, the triple this uses a 168-bit key, but actually behind the scenes what this means is that it's going to make use of 3 keys, each of them being 56-bit in length. So triple this can do 3 time encryption using the this standard, or it can do 1 time encryption, then decryption, then encryption. So it depends on implementation. And finally, the last known and most secure algorithm is going to be AES, which stands for Advanced Encryption Standard. And we have 3 versions for this algorithm. It's going to have either the 128-bit key, 192-bit key, or 256-bit key. Of course, this is the most secure one, not only because it has the largest key size, but also because it's the newest algorithm in there. And of course, AES has a lot of variations. It's not a discussion. It's a CCNP topic. Now, another less commonly used symmetric algorithms, which are very weak and not that commonly used, is going to be Seal, IDEA, Blowfish, or Serpent. And of course, it's a lot more of them out there. Now, as you're going to see the use case of symmetric algorithms, because they are very efficient and very cheap to do the encryption and decryption of symmetric algorithms in hardware. It means that we're going to make use of those algorithms to secure VPN traffic through an IPsec or SSL VPN tunnel. So traffic flowing back and forth to the IPsec or SSL tunnel is going to be secured using symmetric algorithms. And likewise, because it's also cheap and easy to deploy in hardware, it's also, so the securing IPsec or SSL VPN traffic means to secure data in transit, but also we're going to secure data at rest, which means the same algorithms are going to be used to secure folders or hard drives or application containers. So like on your PC, you may choose to encrypt a single folder using AES, or you may choose to encrypt the whole drive using AES or triple this, or you may choose to, for example, encrypt only a certain portion of the database, a certain table, or a certain application container, or whatever you want to encrypt using symmetric algorithms. So mostly symmetric algorithms are going to be used to encrypt and decrypt data in transit or at rest, because it's easy, cheap, scalable, and has performance to be deployed in hardware. Now, asymmetric algorithms, commonly used ones, are going to be RSA, which stands for Rivet, Shamir, Edelman, which is the those 3, let's say, men have invented. Actually, I'm not sure if there's a woman in there. I think it's only 3 men. So Rivet, Shamir, and Edelman is actually the name of the people that invented the algorithm. We have the DSA, which stands for Digital Signature Algorithm. The DH, which is going to be the Diffie-Hellman algorithm. Those are like the most commonly used algorithms from back in the days. And then we also have the newer, let's say, suite of algorithms, which is called ECC, elliptic curve cryptography, which ECC is gonna nowadays and more and more moving forward is gonna replace Diffie-Hellman with elliptical curve Diffie-Hellman. ECDH is gonna replace DSA with elliptic curve digital signature algorithm. They have not implemented the elliptic ECRSA, so there is not a variation of elliptic curve for RSA algorithm. That's because the achievement was not, let's say, from the mathematical point of view, there was not that big of an achievement, so they chose to not implement that functionality. So elliptic curve cryptography only supports, or you're gonna see the implementation to support the Diffie-Hellman version of elliptic curve and the DSA version of elliptic curve, but not the RSA version of elliptic curve. Now, asymmetric algorithms key sizes vary in length. Typically, it's going to be with a size between 160 and 4096 bits, but of course, it can be even larger. It can be 32,067 8 bits in length, or even more. Now, there's another link in here on Wikipedia which I want you to look at, because as I stated, if you look at this table in here, because as I said, you cannot compare, you might state that asymmetric is much more secure because the key size is bigger, but you cannot compare asymmetric algorithms with symmetric algorithms because they use different mathematical functions behind the scenes. And this table in here is used to show you a one-to-one mapping and an approximate equivalence in security strength between symmetric algorithms as compared to asymmetric algorithms. And on the first column you have symmetric algorithms with standard key lengths 80 bits, 112, 128, 192, 256, for example. And then on the other two columns you have the asymmetric algorithms, most commonly used key lengths, with of course both the elliptic curve version and the regular version of the algorithms. And as you can see, mathematically speaking, a symmetric encryption algorithm with a key length of 256 bits, which is AES-256, the most secure one, is comparable in strength security-wise with an asymmetric algorithm with a key size of 15,360 bits, or is comparable with the elliptic curve key length of an algorithm with a size of 512 bits. So that's why you cannot, as I stated, because they use different mathematical functions, you cannot say that asymmetric algorithms are going to be better than symmetric. Because as we're going to go throughout the day with the VPN section, we're going to better realize that we use symmetric algorithms for different purposes than we use the asymmetric algorithms. Now, if you wonder why did we invented another type of asymmetric algorithms, which is going to be the elliptic curve algorithms, is because, as you can see, the elliptic curve version of the asymmetric algorithm, if we use an algorithm with a key size of 512 bits, it provides equal security with a regular asymmetric algorithm with a key size which is 10 times bigger minimum. Or not even 10 times, it's much more than that. So with a key size of 15,260 bits in there. So you can imagine that nowadays with more and more mobile devices, running in the processor of whether in the hardware or the processor of a mobile device, a smartphone or tablet, asymmetric decryption back and forward on a tablet, if the key size is huge, is 15,360 bits in length, is going to severely consume the battery of that mobile phone or of the tablet. So that's why we came up with a better algorithm which provides pretty much the same security strength in there, but the key size being way shorter, so we don't consume resources and batteries on our mobile devices nowadays. I mean, you would want your smartphone, when you bring up an IPsec tunnel, like the battery to be consumed instantly, just because it has to run behind the scenes. It has to dedicate huge processing power, which means battery consumption for that huge asymmetric key length in there. So that's why more and more the elliptic curve version of the asymmetric algorithms are going to replace the traditional asymmetric algorithms as we move on. Now the use case of asymmetric, so we said that the use case of symmetric algorithms is to secure data in transit or at rest. The use case of asymmetric algorithms, we're going to speak more in the VPN section, is that we're going to use these algorithms for key establishment in IPsec SSL VPN, which means as we're going to move in that section, you're going to see that for an IPsec or SSL VPN tunnel to be built, the two peers of the VPN tunnel IPsec or SSL, they have to securely negotiate the keys which are going to be used to protect data, to secure data being sent to the IPsec or SSL VPN tunnel. So that the negotiation process between the VPN gateways is going to be secured using asymmetric algorithms, not symmetric algorithms. So most of the times the asymmetric algorithms are going to be used to secure the control plane of the IPsec or SSL VPN tunnel, so that the two those algorithms are going to be used so that the VPN peers securely negotiate the same keying material, like the same encryption keys back and forward, securely without having to send those keys over the wire in between, because we don't want somebody in transit to actually get their hands on the encryption keys as we build the IPsec or SSL VPN tunnel. And also we're going to use these algorithms for digital signature. We'll speak in more detail when we go to the PKI chapter in there. But as I said initially in here, regardless of the algorithm being used, DSA, RSA, Diffie-Hellman, elliptic curve, there are always two keys involved, always. It's just a difference in the algorithm and what are the capabilities of that algorithm and for what scope we can use that algorithm. But otherwise, all of them make use of the same two keys. The public key, which is always shared, it's going to be publicly advertised, that's the name. And the private key, which is never shared, it's kept secretly on the owner, that's the name of being called the private key. Now, cryptanalysis, if cryptography is the let's say science of providing security to traffic in transit or at rest, cryptanalysis is going to be not really a science, but there are methods to find weaknesses or insecurity in the cryptographic techniques, thus permitting one attacker to obtain the plain text data. Like what this means, as I'm sending traffic, in between my VPN gateways, and I want to provide both encryption so the traffic is not readable in clear text, and both hashing using the keyed method to make sure packets are not modified unauthorized in transit, the attackers may want to grab their hands on the packets and be able to decrypt the packets or make unauthorized modifications without us being aware of that. So commonly used or commonly known cryptanalysis attacks are going to be brute force, known plain text, ciphertext only, chosen plain text, chosen ciphertext, and the birthday attack. Let's take a quick look at each of those. Now, the brute force attack, it means that the attacker has only access to the ciphertext, to the encryption, to the encrypted packet, and using brute force is going to try to decrypt the packet, which means that he's going to try and he's going to try all possible keys against the ciphertext value to be able to at some point end up with a plain text packet. Because the security of the encryption of symmetric encryption does not reside that the key is something magic which nobody knows. Because as long as you know the algorithm and the key size, which is like 56-bit or 256-bit, then the key size, the key space, the key space, all possible keys. But the challenge is to have enough computational resources and enough time to be able to try the ciphertext data against all possible combination of the decryption keys and end up with a clear text data. Which, technically speaking, like nowadays, except quantum computing, a regular computer to break AES could take like hundreds or a lot of years to actually be able to take all of the possible keys, the encryption keys, and parse the ciphertext data against all encryption keys and end up with the clear text data. So a challenge to decrypt the packet is not to magically know the key. Of course, that's going to be ideal if you know the encryption key. But if you don't know the encryption key, one way is going to be the brute force attack, which means to try all possible keys against the ciphertext, and hopefully at some point you're going to be able to decrypt the packet. Now, with the current processing power, this can be cracked fast enough, so that's why this is no longer recommended. And also because triple this is less, let's say, performant in hardware and has some limitations. That's why also triple this should not be used in general, and that's why we should use AES. And with AES, the bit size doesn't really affect the performance of the encryption in hardware, the version of AES. Another attack is going to be known plaintext. And like in the case of brute force, the name of the attack tells you exactly how the attack is going to be performed. Known plaintext, it means that the attacker has partial information about the plaintext, but not full information. So it's a variation of the brute force attack, but as additional information, the attacker knows partially what is the clear text data content, but not all of it. So in the brute force attack, the attacker only gets his hands on the encrypted packet. He has no knowledge about whatever was the clear text data. In known plaintext, the attacker gets his hands on the encrypted packet, but also has knowledge of partially what is the clear text data, which of course is going to give him a better chance with a brute force attack by knowing, partially what is the clear text data, because by making some kind of, fast analysis and statistical computations, he's going to possibly end up faster with the decryption key to decrypt the packet. So the attacker in this case has knowledge not only about the ciphertext, the encrypted packet, but also partial knowledge about the plaintext which was injected in the encryption algorithm. Ciphertext only, again, the attack is very self-explanatory. It means that what the attacker does is going to capture multiple ciphertext packets, so not only one, as it was in the case of brute force. It's going to capture multiple ciphertext packets encrypted with the same key, and using statistical analysis is going to try to find the encryption key as fast as possible. So it's not a brute force attack, but the attacker captures a lot of encrypted packets with the same key, and then using statistical analysis is going to try and shorten the key space from the huge amount of possible keys values to a shorter number of possible keys, which then he can try against the ciphertext to hopefully decrypt the packet. Chosen plaintext, again, the attack is self-explanatory. The attacker, what it does, it has now access also to protected network, so it chooses various plaintext for encryption, observes the ciphertext, and tries to identify the encryption key. So what this means is that in chosen plaintext, if we consider back again that VPN tunnel in there between those two sites of our company, and AS8V and Router 1 have that VPN tunnel built in there, it means that the attacker in here, let's use the attacker with black, the attacker captures all encrypted traffic being sent in the IPsec tunnel. So the attacker captures all of the encrypted traffic, encrypted, all packets encrypted with the same key, and also the attacker somehow has access in the inside network, so the attacker also knows what was the clear text traffic, which was injected in the tunnel to be encrypted. So the attacker knows the clear text data fully. The attacker also captures the encrypted packets fully. He has access to both the input and the output, What's missing is the encryption key. So that's why this is called chosen plain text in there. So the attacker can actually choose its own plain text value to be injected in the encryption algorithm, and then by looking at the output, the output is going to be the ciphertext, he's going to be able to, by different statistical computation mathematical algorithms, to be able to maybe quicker identify the encryption key. Chosen ciphertext, it's a again, the name is self-explanatory. Now the attacker, what it does, it chooses various ciphertext for decryption and observes the plain text and tries to identify the decryption key. So now in this case, what the attacker does is gonna take multiple encrypted packets, is gonna capture the encrypted packets, then let the routers to decrypt the packets, look at the output, and by comparing again, the output is going to be the clear text data, and the input is going to be the ciphertext data, and comparing both the input and the output between multiple packets being encrypted back and forth. Likewise, it's going to try to do some kind of statistical analysis, mathematical functions in there to be able to quicker identify the encryption key without performing a brute force attack. And finally, the birthday attack is going to be an attack against hashing algorithms. It is based on the probability that two people in a group of 23 people have the same birthday, which is above 50%. So chances are that if 23 people meet up in a group, chances are above 50% that two people have the same birthday date. So based on this statistical mathematical function, it means that, as we said before in hashing, it means that there are chances that two different inputs, as you put those two different inputs in a hashing algorithm, chances are they're going to provide the same output. So the birthday attack is going to be a type of a collision attack against hashing algorithms.